In this first video, we're going to be reviewing logic, sets, and proofs. So we're going to first begin with a discussion of propositional calculus. Now, all the material in here should be a review. If it's completely unfamiliar to you as we discuss it, go back and review the Discrete Mathematics Uncovered series. A statement is a thing that's either true or false. We can typically represent it with a single letter. They can be conjoined or modified using a bunch of rules. For example, we can negate a statement. If the original statement is true, its negation is false, and vice versa. We can conjoin two statements with an and, either as a word or a symbol, and this new statement can only be true if both of its individual arguments are true. If either one of them is false, then this conjunction is false. We can also disjoin or use the word or, and this statement is true if either one of the two statements is true. If both of them are false, then this new disjunction is false. We can make an implication, P implies Q, or if P then Q, or just use this arrow. The argument on the left is called the hypothesis, the one on the right is called the conclusion. The only way for an implication to be false is to have a true hypothesis and a false conclusion. When the hypothesis P is false, the statement is true and it's said to be vacuously true. We also have logical equivalence, one logical statement P being equivalent to another Q. This is a sort of meta statement. It's a statement about the underlying statements. The overall claim P is equivalent to Q is true when the two things are either both true or both false at all times they are the same as one another. They can never be different. And this is what it means for two statements to be logically equivalent. We can also talk about sets. So sets are a collection of elements. We usually have braces on the outside and we separate elements by commas, but we can also just use capital letters to represent sets. The universe, represented with a capital U, is all elements that can be discussed in any given context. This acts as a prohibition on talking about irrelevant objects. For example, if we're making claims about numbers, we don't want an illegitimate object to be something like apple. We can make new sets out of existing ones through a bunch of operations that are kind of analogous to our logical operations. We can take the union of two sets. This is the set of all elements that are either in A or are in B. We can take the intersection. This is the set of all things which are in both A and B. We can take the complement of A. This is everything that is in the universe but is not in the set A. We can also make statements about sets. Fundamentally, we want to talk about something being an element of a set, and we use that symbol right there. This is a claim about an element X and the set A. If X is an element of A, this is now a true claim. If X is not an element of A, then this is now a false claim. We can say A is a subset of B. This is also a statement. It's either true or it's false, and it asserts that if something is in the set A, then it is in the set B. So this claim can be true or false depending on the sets in question. Fundamentally, it's a quantified conditional statement. Okay, we can also talk about product sets. This is collections of ordered pairs. The product set A times B is the collection of ordered pairs where the first element is in the first set A and the second element is in the second set B. Order really matters. Or we can talk about the power set. This is a set of all possible subsets of A. Doesn't come up quite as often as product sets, but it is something we should be familiar with. Now we can move on to a discussion of predicate logic. Again, we're just quickly reviewing the greatest hits, so to speak. So we're interested in statements that depend on elements of the universe. For example, if I say X is even, on its face, this isn't even a statement because X is a letter, but we kind of understand that X is supposed to represent an integer, but it depends whether X is a certain type of integer or another, whether this is true or false. Until the integer X is chosen, it's not even really a statement. Predicate statements are things like this. Okay, so we could make a statement, capital E of X, and that could represent X is even. It only becomes a statement when a certain variable is given a value. Predicate statements are not themselves statements. Remember, X is even depends on X. So just writing X is even is neither true nor false until you make a choice of X. But what we can do is we can quantify them. Okay? We can use this symbol here, this upside down capital A. This means for every choice of the variable x, the statement p of x is true. This is now either true or false without actually substituting a value for x. Either for every x, p of x is true, or that's not the case. We can also use this backwards capital E. There is some x for which p of x is true. And again, without choosing x, this on its whole is now either true or false. Either there is some x for which p of x is true, or there is not. So we can also make truth sets. So if I have a predicate statement p of x, the truth set is all the elements of the universe for which that statement is true, and we denote it as follows. Predicate statements and quantifiers have their own fairly intricate rules for use, including how they interact with negations, conjunctions, disjunctions, etc. Okay, so how do we deal with predicate statements, quantified statements, when we want to construct proofs? So typically what we want to do is determine whether a statement is true or if it's false. Okay? And if we can do so in a finite list of permitted steps, that's called a proof. If a statement is universally quantified, for every x, p of x is true. If that is true overall, it has to be true for every single element of the universe. So what you have to do is you begin your proof by saying, suppose x is arbitrary. Suppose x is in the universe, but we do not specify which one it is. Now, because this is supposed to be an arbitrary element of the universe, the variable you use must not be used in the current proof. Okay, so as long as you use a new symbol that hasn't been used for anything so far, then this really does represent something arbitrary. You can't reuse a symbol that already has a meaning within the proof, because then it doesn't represent a completely arbitrary element. It represents the one that you were already talking about. And that care in using a new variable when you want to have an arbitrary element allows a sort of formal logical step called universal generalization, which will say that yes, this really does represent anything in the universe. If, however, you already know that a universally quantified statement is true, then what you're allowed to do is write that statement for any choice of variable, even if that variable's already been used. If for all x, p of x is true, then even if x exists somewhere else as a variable, then we can write p of x because it's true for everything, it's true for that one. That's called universal instantiation. In contrast, if you just want to show that there exists an x for which p of x, then it's actually okay to use a very specific choice. If you can show that the statement p of x is true for one specific choice of variable, then you can use a technique called existential generalization to say, well then yes, there does exist something for which the statement is true. In contrast, if you know that there is something for which the statement is true, and you want to write it's true about one particular element, that has to be a new variable that has not yet been used in the proof, because you only know the statement is true for one thing in the universe, but you don't really know which one. So if you've already been talking about the variable t, and you know there is something for which the statement p is true, you don't know that it's that one you've already been talking about, so you can't just write p of t. Okay, and this is known as existential instantiation. So why do we have all these various restrictions about, using a new variable or not? Suppose we know that there is some number which is even, and we also know there is some number which is odd. Let's just assume that we do in fact know that. So we know there exists an x for which e of x, assuming e of x means it is even, and there exists an x for which o of x, assuming o of x means that it's odd. So these are both true statements. There does exist a number which is even. There does exist a number which is odd. But if we used the same variable for both, we could write something like t is a number which is even and t is a number which is odd. But this would imply that t is a number that's both even and odd, and those numbers don't exist. So just because there exists something that's even and there exists something that's odd, you can write e of t. At this point in our discussion, t is a variable that has never been used. So if there exists a number which is even, we can give it a name. Let's call it t. But now that t is a variable that has been used, I can't use it for this statement here because it's already a special variable. It's the one thing that we know happens to be even, so I can't use it for another existential statement. So instantiating existential statements needs to have that sort of restriction. Okay, and suppose, conversely, we're able to show that e of 6 is true, meaning 6 is a particular choice of variable for which this statement is true. 6 is an even number, and that is, in fact, correct. We can't use this to claim that every integer is even. Just because you show a statement is true for one specific choice of a variable does not mean it is always true. So, if you want to show that a universally quantified statement is true, it's not enough to just show p is true for one choice. You have to do that more general proof technique of saying, suppose x is an arbitrary element, a new variable that's never been used for anything, and still manage to show that the statement is true. Well, then it must have been true for everything. Okay, in proving statements, there are a couple of different techniques that are commonly used. Okay, the first is called a direct proof. This is the most straightforward way to prove a statement, but it only applies to conditional statements, P implies Q, or if P then Q. Remember that the argument on the left, P, is called the hypothesis, and the one on the right, Q, is called the conclusion. A direct proof begins by saying, assume the hypothesis is true, then you perform a bunch of steps and show that the conclusion Q must be true. That's a direct proof. Okay, what steps are or are not allowed is sort of a matter of logic. Okay, we're not concerned with writing very formal two-column proofs in which we formally list out every individual operation and every individual justification. That's really not done in practice. Rather, what we're going to do is we're going to be doing kind of a fluid written style where we write sentences and make arguments. But behind all of the arguments we make, there are these formal rules. You may remember them from discrete math or other logic courses: modus ponens, modus tollens, universal modus ponens, disjunctions, specialization, all this kind of stuff. It's all floating around, but we don't really call it that anymore. Very few people actually do. Well, if that's direct proof, assume the hypothesis, derive the conclusion. What's indirect proof? Instead of trying to show that your claim is true, prove that it can't be false. Remember, statements have to be one or the other. So if it can't be false, it must be true. So the goal is to assume the negation of the thing you're trying to prove. Whatever the statement is, and it can be a big nasty compound statement, but we're just going to write it as a single letter here. If you want to prove something is true, you assume the negation. Then what you do is derive some sort of contradiction, a statement that must be false. So if assuming the negation of your assertion, P, leads to a contradiction, then the negation of P can't have been true. In other words, P cannot be false. If P can't be false, it must be true. Okay? It doesn't actually matter which contradiction you derive. If you derive any contradiction at all from the starting assumption that P is false, that will itself necessarily imply that P had to be true. If it can't be false, it must be true. That's the basic summary of indirect proof. Assume what you wanted to be true is actually false and derive some sort of contradiction. Okay, we don't distinguish between two very similar techniques, proof by contradiction, proof by contraposition. We call them both indirect proof. Proof by contraposition says, if you're trying to prove the conditional statement P implies Q, a direct proof would be assume P is true, derive Q is true. Proof by contraposition says, assume that Q is false, derive that P is false. So not only are you going in the opposite order, you're starting from the conclusion and working back towards the hypothesis, you're working with negations instead. That's a proof by contraposition, and it's essentially the same as an indirect proof as described above. Okay, what it amounts to is a direct proof of what's called the contrapositive of the original statement, which is logically equivalent. This statement here is logically equivalent to that one. Okay, these are called contrapositives of one another. And if you wanted to prove this directly, you would assume this hypothesis not Q and then derive this conclusion not P. So proof by contraposition is just a direct proof of a logically equivalent contrapositive. Okay, alternately, a direct proof could begin with P. Okay, you would start by assuming P, and then you would need to derive Q. And if you know you need to derive Q, what you could end up doing is say, well, I don't know how to do it. Let's do an indirect proof. I want to show Q is true, so I'm going to assume Q is false, and now get a contradiction. One of the contradictions you might derive is getting not P. That would exactly contradict your original assumption of P. And you can combine these two things together then to get P and not P, which is definitely a false statement. Okay. Proof by contradiction, proof by contraposition, we're just calling that all indirect proof. Well, there are other proof techniques. For example, proof by cases. This is a way to derive a specific conclusion, Q. This thing you're trying to show, Q, hopefully you can establish it as the conclusion of a bunch of different conditional statements where the hypotheses are different, note, but the conclusion is all Q, the thing you're trying to show. Then what you show is among all the hypotheses that you used, at least one of them has to be true. In other words, the disjunction P1 or P2, etc., is true. At least one of them holds. Well, at least one of the hypotheses is true, even if you don't know exactly which one. And any one of them would imply Q, and therefore what you conclude is that Q must be true. In practice, you usually only have two cases. Okay, there's not a horrendously long list of statements to prove here. Usually there's just going to be two different conditional statements and a disjunction of two hypotheses, but there might be 3, 4, or even more. So here's an example of a claim. For any integer x, x squared is bigger than or equal to 0. The square of any integer is bigger than or equal to 0. This makes sense to us. We're used to it, but can we prove it? Well, we started with a claim about any integer, so we need to use a variable that doesn't have any meaning yet. It's only appeared in our assertion, but not actually in our proof yet. So we can use x. Let x be any integer at all. If I assume the integer x is bigger than or equal to 0, then if I multiply the inequality by x, well, x was not a negative number. How do I know that? I just assumed that x is bigger than or equal to 0. So if I multiply by a non-negative number, I don't have to flip an inequality, and I get x squared is bigger than or equal to 0. In other words, we've proven the conditional statement, if x is bigger than or equal to 0, then x squared is bigger than or equal to 0. But if I assume x is less than or equal to 0, well, now I'm multiplying by something that is less than or equal to 0. So I'm going to multiply this inequality by x, but I have to flip the inequality because I'm multiplying by a negative number. So I get x squared is bigger than or equal to 0. In other words, if x is less than or equal to 0, then x squared is also bigger than or equal to 0. Notice we had the same conclusion for two different conditional statements. Here's one hypothesis, here's the other. And now what I can certainly state is either x is bigger than or equal to 0 or x is less than or equal to 0. This is just a property of inequalities. Okay, so of the two hypotheses, at least one of them must hold, even if, because x was totally arbitrary, I don't actually know which one of these holds. Because I didn't pick x to be a specific integer, I didn't pick it to be 12. Okay, I didn't pick it to be -8. I don't know which one of these is true, but I do know no matter what one of them is. If the first one is true, then I get my desired conclusion. If the second one is true, then I also get my desired conclusion. So even though I don't know which one of these holds, at least one of them does, and therefore I say in either case, the conclusion holds. This is an example of a proof by cases. Establish a couple different conditional statements and then show that at least one of the hypotheses holds. And those conditional statements all have the same conclusion, well, then you get to conclude what you wanted. The last proof technique that we're going to use a bunch is called proof by induction. Okay. This is specifically a way to prove a statement universally quantified over the natural numbers. In other words, for any x, p of x is true, where x ranges over the natural numbers 0, 1, 2, etc. Notice this isn't all integers, it isn't all real numbers, it's very specifically the natural numbers. There's two major styles of proof by induction, weak induction and strong induction. For weak induction, first you establish the claim is true for 0. You make a very specific choice of x. You say of all of the x's I could have picked, any natural number, I'm very specifically choosing 0. Okay. Since we want the statement to be true for all natural numbers, hopefully we can at least show it's true for 0. This is called the base case of the inductive proof. Next, establish this conditional statement. If you assume the statement is true for n, can you then show that the statement is true for n plus 1, where n is not a specific natural number, it's any natural number. Okay, so generally you're going to do this by assuming P of n is true. You're going to prove it directly, and this is called assuming the inductive hypothesis. And then you're going to derive P of n plus 1. Once you have both of these things proven, the base case, P of 0, and the inductive step, P of n implies P of n plus 1. Okay, now I've proven both of those things. Altogether, it now must be true for all natural numbers. Okay. Strong induction starts slightly differently. Rather than simply showing P of 0 is true, you show P of 0 up through some specific k. Okay, you actually pick this. It might be 5, for example, in which case you show P of 0, P of 1, P of 2, P of 3, P of 4, P of 5 are all true. These are all now various base cases. Then you assume that all P of whatever are true up to a certain point, at least as far as the final base case you proved, and then you derive the same thing, P of n plus 1. By proving more base cases, okay, you had to prove a bunch of base cases, you get to make a stronger inductive hypothesis. Instead of just assuming P of n, you assume everything up to P of n is true. This is a strong inductive proof. It has more work in the base case step, but allows you to make more assumptions at the inductive step. Once you've done that, however, you have finished the inductive proof that this claim is true for all natural numbers. So this was just a review of a bunch of notation that hopefully we're at least vaguely familiar with. How do we notate statements with disjunctions, conjunctions, arrows, negations? What are the basic styles of proof? Direct, indirect, proof by contradiction, proof by cases, and inductive proof when doing proofs over the natural numbers. It's not necessarily assumed that you have immediately recalled all of the details of these things, but they should at least be familiar terms. If you've never heard the phrase proof by induction, then some things are not going to make sense later. Okay, if you've never heard of what the natural numbers are, just look it up. You can Google it or Wikipedia it. Okay, so this is just a review of some background terminology that it's kind of assumed you're familiar with before starting this course.